Okay, so heading into some of these problems that we're going to do, this is your NASA table, and we're going to go over what each of these are, and then we're going to continue on. Once you know how to do a NASA table, you can then draw the Lewis dot structure. That's what we went over in detail in the lecture today, and will tomorrow. And then from there, you're going to go to your homework, and you're going to then drill down and use that Lewis dot structure to figure out some other things. And what you're going to figure out is shown over here on the right. So what the lab takes you through, the pre-lab questions essentially got you to here, to the Lewis dot structure. And then what you're going to do next week is continue that and continue it all the way down to molecular geometry. The lab doesn't go all the way to polarity. See, name of molecular geometry, molecular geometry. So what I want you to see from these, so you can see that I give you a formula, and then you're going to draw a Lewis dot structure. Oop, I didn't want to go through there. Okay, so then there's the Lewis dot structure. Let's try not to cover up that writing. Yes. And so what I don't ask you to show me is the NASA table, but I know you're going to have to do that to get here. Okay. And then you're going to take your areas of high electron density, and you're going to use that to determine the electronic geometry. Better switch colors, it's getting messy. You're going to do the electronic geometry. And then after you know the electronic geometry, you're going to count the number of lone pairs. And then once you know the number of lone pairs, you can then determine the molecular geometry. And what we don't cover in the lab is the polarity. We are in the lecture, so this is going to be a lecture only. So I want you to see what we've talked about earlier, this cascade here, that this is actually that cascade where I'm just prompting you for this information. And the reason I'm doing that is this is the information you need to get here, and then this is the information you need to get there, and I'm going to put a hook through your jaw and drag you through the whole process all the way down there. Okay. So you know where this is at and what this is all about. Right. Might need that again later. Okay. So with that, the first thing we want to do is we want to revisit the Lewis dot structures, but I want to talk a little bit about the needs line and expand on what I talked about in the lecture. So for the most part, we're going to deal with the structures that are shown here in green, and you will recall that those are called the representative elements. And you can assume, and we can also treat hydrogen like it lives here. I really like to pretend hydrogen lives here, and it does act a lot of times like it lives there. Okay, and some periodic charts will actually draw it a light gray one there, just to let you know that. Okay, so essentially anything over here that's larger than carbon, any of these, you assume it needs 8 electrons. And for those of you who haven't had the lecture that are going to attend tomorrow, it'll be covered there. Anything from carbon up that's on this hillside of representative elements, you assume they need 8. Now, everything smaller than carbon, and remember, I told you the way to know how many of the 8 is anything in group 1 has 1 valence electron. Anything in group 2 has 2 valence electrons. Anything in group 13 has 3 valence electrons. Anything that's in group 14 has 4. 15 has 5, 16 has 6, 17 has 7, H is 1, And then anything in group 18 has 8. That's valence electrons. Outer shell, that's what we care about, is just the valence electrons. Okay, so that's what the need is going to be. So let's go over this. So when we did CS2, right? So what do we have here? We have, okay, so let's look at this. So for this, I have what? 1 carbon atom. Oh, that's ugly. And 2 sulfur atoms. Okay, the needs line. My 1 carbon needs how many? 8. How do you know that? Because carbon needs 8. Anything in this block needs 8 electrons to be happy. And each of my sulfurs needs how many? 8. How did you know that? Because sulfur is in this block over here. It's in this block, so it needs 8. So those sum to be 24. Okay, that's the needs line. How many is available? The available is determined by looking at what group it's in. So again, I have 1 carbon. How many electrons does it make available? Well, it's in group 14. Let's look at carbon. It's in group 14, so it needs how many? 4. And that's where I got the 4 from. And I have 2 sulfurs, and each one makes how many available? Not needs, but available. Remember the needs line. Yes, this needs line is from the octet rule. Which big block is it in? Oh, can't go backwards. Why not? Timeout. Okay. Really, my Control Z isn't working? Okay, I'm going to have to do that manually. Okay, so this 8 and this 8 come from looking at what's in this block. And this available comes from the group number. So each of my 2 sulfurs needs how many? Well, sulfur is in group 16, so it needs 6. So that's where that comes from. And you add those up, and you get a total of 16. Right. Okay. The reason we're doing that is all we really care about so we can do this is we need to know what's paired. The only reason I'm doing this table is so I can do my math to figure this out. Ultimately, the only thing I really care about here, I'm doing all that to get this number and that number. That's what I'm using. Yes, these are means to an end. That's the end. Those are the prize. So let's see. So if I have 8 shared electrons, the S stands for shared, how many bonding pairs do I have? Remember, a shared pair makes a bonding pair. So if I have 8 electrons, I have to divide that by 2. And that tells me, because there's 2 in a pair, 8 divided by 2, I can make 4 pairs. 4 what? Bonding pairs. And then what do I have left? The last A means, remember, alone. So if I have 8 electrons that are all alone, how many lone pairs do I have? 8 divided by 2 is 4. Okay, so this is what I really care about, is right here. Okay, now here's where I flesh it out. That's the first thing. Stop. So to get to here, you have to do 2 things to get to your Lewis dot structure. 2 things. Count them 2. The first thing you have to do is you must do the NASA table. And the second thing that you do is you got to make a skeleton. Okay. You got to make a backbone, a skeleton. And you can do these in either order. It doesn't matter. These can be done independent. But what these 2 things I have circled are going to do is bring them together. Okay. So let's figure out. Now this was the final answer. So let's pretend we hadn't got there yet. Let's show you how we got there. So I'm going to do it on this one so I can erase it here in a minute. Okay. Is that good? Yep. Okay. And let me try one more thing. Does this even work? Oh man, this is pretty rough, folks, because I've got like 6 programs going. It's a wonder it's even working at all. Okay. So what is the skeleton? It's where you take one of these and 2 of these and you just draw them together with a stick. So I'm going to guess my structure looks like this. Okay. Why did I put the C in the middle? Because the thing that's farthest away from fluorine, remember that, the thing that is farthest away from fluorine is the thing that you try to put in the middle. Except it can't be hydrogen. It can't be anything smaller. Well, it can't be hydrogen. Okay. Except for hydrogen. You'll see why in a minute. Okay, so fluorine. So let's see, what do we have? Sulfur is pretty close to it. It's 2. And let's see, carbon is 1, 2, 3. So I'm going to go with carbon as the central atom. It's furthest away. And what I'm doing, for those of you who haven't attended the lecture yet, is that's just a guess at which one's most electronegative. If I don't give you numbers, you have to guess it's the thing furthest away from fluorine. Because, as you may remember, electronegativity increases going up the periodic chart and across to the left. What that means is the further away you get from the left top corner fluorine, the bigger the difference, and the less electronegative you are. Okay, so I'm going to guess it's this way. Now let's place it. So what do we do here? The first thing we want to do, I'll switch colors so we can see this. The first thing we want to do is place our bonding pairs. How many bonding pairs do I have? 4 bonding pairs. My skeleton's already got 2. You can see that. See, there's 1 bonding pair. There's 2. The only way you can connect atoms is to use at least 1 bonding pair. That's what you're going to do. It might need more than 1, but it needs at least 1. Okay, so I need 4. So I got to place 2 more bonding pairs between the atoms. So I'm going to place 1 there and 1 there. Yes, I could have placed 3 here and only 1 there for a total of 4, but I would have just a lot easier if you just try to make them symmetric like that. Okay, so there we go. So my 4 bonding pairs are placed. Boom. See, and now you can start seeing how this is already starting to look like the correct answer. Okay, now I have to place lone pairs. What's the rule for placing lone pairs? Place them outside in. Now it's getting all glitchy. I knew it was going to get glitchy. All right. Place them outside in, which means I'm going to place my lone pairs on these outside, and anything that's left over, I'll dump it on the central atom. This thing here, of course, is called the central atom, the thing that everything's hanging off of. Okay, so how many electrons did we say sulfur needs? 8. So let's put 8 electrons on it. 1, 2, 3, 4, 5, 6, 7, 8. Why do I stop at 8? Because we've said earlier, I want to see 8 on my sulfur, so it obeys the octet rule. Hopefully you can see the 8. A strike mark counts as 2. A bonding pair is a pair of electrons. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's good. Can I put any more on it? Nope, because I'll have more than 8. Can I put any fewer on it? Nope, because I have a number than 8. I need exactly 8. Okay, how many bonding pairs did I place? Let me see, that's 1 pair, 2 pairs. I just placed 2 of the 4. I have 2 more to place. Where do I go? To the other outside. Remember, the rule is outside in. So let's start placing some more. 1, 2, 3, 4, 5, 6, 7, 8. Okay, stop. I can't put any more on that, so I'll stop and take inventory. How many did I just place? 1 bonding pair, 2 bonding pairs. I placed 4 electrons, but only 2 pairs. And since I'm counting pairs here, that now goes to 0. And I'm all done. So this should be my Lewis dot structure right there. All my bonding pairs have been placed and all of my lone pairs have been placed. Boom. Looks like we got the right answer. But let's check to make sure. How do you check? Before you write your final answer, you make sure this is true for everything because that was your target. So ask yourself, does my carbon feel 8 electrons? So let's see if I can do this and we can maybe, okay, does it feel 8 electrons? Let's see. Let's draw a circle around this. Let's try that again. I have a severe lag. Okay, does it feel 8? 1, 2, 3, 4, 5, 6, 7, 8. Check. Feels 8 electrons. That's good. Does each of my sulfurs feel 8? Well, let's see. There's one of my sulfurs right here. And let's count them. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that one looks good. So that one checks out. All I have to do is to get one more sulfur to work out. And that was so slow, I'm going to have to do this with a mouse. At least it writes faster. Okay, and how many does that have? 1, 2, 3, 4, 5, 6, 7. So everything feels 8. So this is good. So those two check out. Everything is right. My structure is consistent with my line 1. That is my Lewis dot structure. That's how you get there. Okay? That is. So what we just did just then was this. Okay. I want to do water so I can show you an exception to the rule. Here we go. What is the N line going to be here? Let's see. So what do we have here? And I'm going to need to do this thinner, I think. That was pretty thick. Yeah, that'll work. Okay, so let's do H2O. What is the need line on there? Geez, I might could type better than that. That's pretty sad. So what's my need? My need is equal to what? I have 2 H's. My need is equal to, I have 2 H's, and each H needs how many to have a full outer shell? It doesn't need 8. It only needs 2. So I'm going to have to explain that to you. But let's go ahead and finish this up first of all. And I had 1 oxygen. And how many does it need? It needs 8. Okay, remember, everything is going to need 8 except for the things that are smaller than carbon. And you will note that H is smaller than carbon. So the question is, how did I know hydrogen only needed 2? And here's how you do everything smaller than carbon, which there's only 5 things smaller than carbon. You can neglect helium. Why? Because helium doesn't form a compound. If it doesn't form a compound, it's not sharing anything. So you can totally blow neon off. Matter of fact, you can blow all of these off. Right there. You can just blow every one of those stinking things off. Because they're not forming compounds. For the most part. Okay. I know when you get to general chemistry, you're going to see that they actually force xenon to make a compound. So there are some rare exceptions, but for the most part, if it's a noble gas, forget it. If it doesn't form a compound, it can't share electron. If it can't share electrons, you can't do it. You can't do this on it because S is shared. Right. Okay. So here's how you know. Here's how you know this was a 2. Hydrogen and lithium, they're both smaller than carbon. They're in group 1. The needs is going to be twice the group number. Twice. So, if this one has available one electron each. Why does it have available? Because it's in group 1. So it has 1, it needs 2. That's why I put a 2 there. If this were lithium, guess what the need would be? It would be 2. Why? Lithium is in group 1 and it's smaller than carbon. Therefore, it needs 2. What if this were beryllium? Be and then O. What would that be? It would be what? My beryllium would need, it has 2, it needs 4. It needs twice as much as it has available. In other words, it's twice the group number, or the last digit in the group number. Okay, how about boron? So this is all there is 4. So hydrogen has 1, needs 2. Lithium has 1, needs 2. Beryllium has 2, needs 4. And boron, take a wild hairy guess. Boron has 3, needs 6. Bingo. And now you're on track. Carbon has 4, needs 8. And see, now you're on the octet rule. And everything after that needs 8. Okay, so let's go back to this. So I have 2 hydrogen. Each one needs 2. I have 1 oxygen. It needs 8 for a total of, let's see if it'll let me go back in this and type. For a total of what? 8, 9, 12. Okay. Now let's do to the available line. I still have 2. Okay. Let's see. I'll have to just, okay. It has available. I still have 2, and it's very important you keep the counting. I always put the number first, and then I put the need or available in parentheses. It's just me to keep my counting. So I have 2 hydrogens, and each one makes how many available? It has 2, and how many it has available? 1. How do you know that? Because it's in group 1, and the group number determines. Okay, and I still have 1 oxygen, and it needs how many? I mean, no, strike that. I know it needs 8. How many does it have available? It makes, since it's oxygen, I look at oxygen, it's in group 16, the last digit, and that used to be called group 6, by the way. The old days, that was actually group 6A. They actually would just call it group 6, okay? Now we got to go by the last digit. So it's basically in group, the old 6A, it's in a group that ends in 6. So it has 6 valence electrons for a total of 6, 7, 8. All right, 8. Okay. So now how did we say we get the shared line? We get the shared line by subtracting the 8 from the 12. And that's going to be equal to 4, yes? Okay, so we got 4 electrons that are shared. And finally, how many alone electrons are we going to have? Well, we're going to have what? We're going to get that one by subtracting this 4. Remember, this 4 is this number minus that number gives you this number. And this number minus this number gives you this number. So 8 minus 4 gives me another 4. So there we go. Okay, that's my electron count. Now I need to break it into pairs, correct? And now I'm going to have to go to writing. Okay, right? So how many bonding pairs can I make out of 4 shared electrons? I can make what? 2 bonding pairs. BPs is the abbreviation for that. Okay, I'll put it in brackets so I know. Because remember, this is what I'm going to use to flesh out the skeleton. Flesh out the skeleton. Okay, and my alone. How many lone pairs can I make out of 4 lone electrons? Well, if I have 4 electrons, I can make 2 lone pairs, and that's all I care about. All this other stuff now is just kind of rubbish. I don't really need it. I'm not gonna cross that one off because I'm gonna come back and use that as my check line. But all this stuff is rubbish now. I only did that to get this. So here we go. So now that's the first thing. I did my NASA table for water. Now I need to do my skeleton. Okay, the thing furthest away from fluorine is going to be your central atom. So Fluorine is here. Well, oxygen is only one away, and hydrogen's way over here. So I'm going to say hydrogen's my central atom, but wait, it can't be, because hydrogen can only have 2 electrons, right? So if it can have only 2 electrons, it can only have 1 bond to it. Well, if you only have 1 bond, you can't be the center, right? It's impossible for hydrogen to be the center. So in this case, oxygen has to be the center. Even though it's more electronegative than hydrogen, it's impossible for hydrogen to be the central atom. So oxygen has to be the central atom. So here's our skeleton. Okay, so here we go. What are we going to do? We're going to place the bonding pairs. You're going to place the bonding pairs, and that's it. So let's start placing the bonding pairs. Ready? Okay, let me get a highlighter. That might allow me to do this better. Maybe even switch colors and knock that down a little bit and maybe make it bigger. All right, so let's see. Bonding pairs. Let's start from the outside. Can we place a bonding pair here? Is there anything wrong with that? Absolutely. What? You can't do it. The key is, do you know why? If you don't know why, I'm going to tell you, and you better not forget it, because I can tell you. So listen to me carefully, because I will see this on the exam. Anytime there's lone pairs on a hydrogen, it's wrong. It's wrong. Why? Because hydrogen needs at least 1 bonding pair to bond, and how many electrons does that represent? 2. And hydrogen can only have how many? 2. That's a maximum amount. So anytime you bond anything to hydrogen, that's it. That's all the electrons it can take. It can't take any lone pairs. Okay? So I got to place 2 bonding pairs. I can't place it on that hydrogen. Can I place it on this hydrogen? No. Why not? Because there's your 2 electrons. Remember, hydrogen can only have 2. And if you look, there's the 2. That's it. Okay. So that's why you got to be very careful with this, is this will guide you, this top line. Okay, well, now we got a problem because we've still got 2 bonding pairs to place. So where are we going to place them? You place them outside in. Once you go over all of your outside groups, any electrons that are left over have to go where? On the central atom. So I'm going to place 1 bonding pair there and the second one there, and that's the only place they can go. Ladies and gentlemen, that is your Lewis dot structure for water. Does it check out? I don't know. Let's see. Let's check out. Dang it. I was hoping it did this for individual thing. Okay, so let's check it out for this. Oh, we'll do the H's first since they're listed first. Okay, so let's circle this H. How many electrons does that H feel? 2. Those 2 right there. And how many did we say we wanted to feel? 2. So this, one of these H's checks out. How about the second one? How many electrons does this one feel? 2 electrons. How many does it want to feel? 2. Boom, perfect. Now you can see why if you put a lone pair, it would be wrong. Let's put a lone pair there. And I would say, how many electrons does this hydrogen feel? You'd say 1, 2, 3, 4. But wait, you said it could only have 2. Why did you draw 4? And then you'd say, well, because I'm an idiot. Okay. Or you'd say, because I forgot. Right. Okay, now here's the big one. My 1 oxygen needs to feel 8. So let's look at oxygen and see how that works out. Let's draw all the way around. Every bond or electron that it touches is what it's using. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. So that's 8. It feels 8 electrons. And how many did it want? 8. So there we go. So that's how you can take 8 electrons, but you can share them in a way that it acts like everything's got the full octet. That's the way it works. So that is your Lewis dot structure for water. And that's your first exception. You're going to have two exceptions. The first exception is what I call the less than carbon exception. Yes? So anytime you have hydrogen, now I've got to switch things here. Anytime you have hydrogen or lithium or beryllium or boron, I can tell you what your needs number is, and it's not 8. Why? Because they're an exception. So remember, boron has 3, needs 6. Beryllium has 2, needs 4. Hydrogen has 1, needs 2. Lithium has 1, needs 2. Okay, so that's your first exception. And if you did carbon, now I'm not going to do carbon, but I will show you carbon here. Let's find another one. It really... all right, we'll draw solid. So this one's going to look like, would wind up looking like this, by the way. And I think a lot of these, so you're going to wind up with basically no lone pairs, none.